Hey, welcome to The Explainer. Today, we're going to dive deep. I mean, really deep, right down to the very heart of matter itself. We're talking about the fundamental building blocks of, well, everything, atoms and molecules. So here's our game plan. We're going to kick things off way back in ancient times with the very first idea of the atom. Then we'll jump into the hard science, the rules of combination that chemists discovered. We'll look at Dalton's huge theory that tied it all together, and then get into the nitty-gritty, the language of atoms, how they build molecules, and finally, we'll tackle the big one, the concept that trips so many people up, the mole. It's going to be a fun ride.
All right, Section 1, the ancient idea of the atom. So, let's start this whole quest with a question. A really, really old question that people have been asking forever.
Yeah, this one. What is everything in the world actually made of? I mean, seriously, think about it. If you break something down and then break it down again and again, what do you end up with? This one simple question kicked off a massive search for the ultimate building block of reality.
And what's really amazing is that thousands of years ago, brilliant minds in completely different parts of the world, in both India and Greece, basically came up with the same idea. It was just a thought experiment, right? They said, look, if you just keep dividing something, eventually you have to hit a point where you can't divide it anymore. A final, indivisible particle. In India, they called it a parmonio. Over in Greece, they called it atomos, which literally means uncuttable. Pretty cool, huh?
Okay, so for a really long time, this was all just philosophy. Just a cool idea to talk about. But then, flash forward to the 18th century, and everything changed. The game was on. Scientists started heading into the lab, and they weren't just thinking anymore, they were measuring. They were discovering the actual rules for how all this stuff combines.
And the first huge rule they figured out was this: the law of conservation of mass. A guy named Antoine Lavoisier figured out that you can't just make stuff appear or disappear in a chemical reaction. It sounds simple, right? But it's a huge deal. It just means that whatever you start with, mass-wise, is exactly what you end up with. Nothing is created, nothing is destroyed.
And we can actually prove this. Check it out. Let's say we take some sodium carbonate, 5.3 grams of it, and we mix it with 6 grams of ethanoic acid. You add those together, what do you get? 11.3 grams. That's our starting mass. Now, after the reaction happens, we weigh all the new stuff that was created, the sodium ethanoid, the carbon dioxide, the water, and guess what? Add it all up, and it's 11.3 grams. Exactly the same. See? The mass was conserved.
All right, so that was rule number 1. Rule number 2 is just as important: the law of constant proportions. Think of it like a recipe. A specific chemical compound, like water, always has the exact same recipe, by weight. It doesn't matter if you get water from a glacier, a river, or your kitchen tap. The recipe is always the same. 1 part hydrogen to 8 parts oxygen by mass.
And you can see how this recipe math works out for different things. For water, H2O, you take the mass of 2 hydrogens and 1 oxygen, do the math, and boom, you get a 1:8 ratio. For something like carbon dioxide, CO2, it's 1 carbon and 2 oxygens. The mass ratio for that recipe simplifies down to 3:8. These ratios are locked in, they're constant. So now we've got these 2 huge clues, right? The law of conservation of mass and the law of constant proportions. They were just sitting there, waiting for someone to connect the dots. And that someone was a chemist named John Dalton. He's the one who took these pieces and built the first real scientific theory of the atom.
And Dalton's theory was a total game changer. I mean, look at these points. He said everything is made of atoms. He said they're indivisible, you can't create or destroy them. He said all atoms of one element are identical. And, crucially, he said they combine in simple whole number ratios to make compounds. This wasn't just a random idea. It was a beautiful model that perfectly explained those 2 laws we just talked about. It all clicked into place.
But here's the thing about science, right? It's always moving, always getting updated. And while Dalton's theory was brilliant and foundational, we eventually found out it wasn't the whole story. For instance, he said atoms are indivisible. Well, turns out they are. We discovered protons, neutrons, and electrons. He said all atoms of an element are identical. Well, we found isotopes, which are atoms of the same element that actually have slightly different masses. So it wasn't that he was wrong, it's just that the picture was more complicated than anyone knew.
Okay, so our understanding of atoms is getting way more sophisticated. The next logical step? We needed a universal language to actually talk about and measure these things.
But that leads to a massive problem. How in the world do you weigh something you can't even see?
Atoms are so ridiculously tiny, putting one on a scale is just not going to happen. So chemists had to get really clever, and the solution they came up with was truly ingenious.
So they said, forget trying to find the actual weight. What if we just compare them to each other? They created a relative scale. They just needed a standard, a benchmark to measure everything against. They picked a really common atom, carbon-12, and they just decided to assign it a mass of exactly 12 units. So that means our standard unit of measurement, the atomic mass unit, or U, is just 1/12 of the mass of that one single carbon-12 atom.
Okay, think of it like this. Imagine a carbon-12 atom is a pizza. We cut that pizza into 12 perfectly equal slices. The mass of just one of those slices, that's our standard unit. That's 1 U. So now, when we want to weigh any other atom, we're basically just asking, how many pizza slices does this thing weigh? It's a brilliant way to measure something so small.
Okay, so we've got a way to measure the atoms. Now let's see how these little guys actually get together and combine to build, well, everything.
The thing is, atoms are pretty social. They don't usually hang out alone. They bond together to form molecules, and there are really just two main types. If you have a molecule made of only one type of atom, like O2, which is just two oxygen atoms stuck together, we call that a molecule of an element. But if you have different types of atoms joining forces, like an H2O with its hydrogen and oxygen, then you've got a molecule of a compound. Simple as that.
Now, writing the chemical formulas for these compounds can sometimes feel a little intimidating, but I'm going to let you in on a really cool trick. It's called the crisscross method. All you need to know are the charges of the ions involved. You literally just take the number from the charge of one ion and make it the subscript for the other, and vice versa. You crisscross them. Then just simplify the numbers if you can. It's a super fast way to figure out the right formula every time.
All right, deep breaths, everyone. We're about to tackle the one concept that gives students the most headaches, the mole. But I promise you, if you stick with me, you'll see that it's not nearly as scary as it sounds. At its heart, it's just a simple counting tool.
Okay, let's just rip the Band-Aid off. Forget all the complicated definitions you might have heard. A mole is just a word for a number. That's it. Seriously, just like the word dozen is a shortcut for saying 12, the word mole is a shortcut for saying, well, a really, really big number. Since atoms are so tiny, we needed a convenient word for counting a giant pile of them, and that's the mole.
And this is that number. It's called Avogadro's number, and just look at it. It's 6.022 times 10 to the 23rd power. It's a number so huge it's hard to even wrap your head around. But this number is the absolute heart of the mole. 1 mole of anything, atoms, molecules, whatever, means you have this many of them. So, this brings up a common question. Why does a mole of one thing weigh differently than a mole of another? Well, think back to our dozen analogy. A dozen apples weighs a lot more than a dozen berries, right? Of course. Even though you have the same number of each, 12, the individual apples are much heavier. It is the exact same logic with atoms. A mole of oxygen atoms weighs more than a mole of hydrogen atoms, for one simple reason. Each individual oxygen atom is heavier than a hydrogen atom. Same number of particles, different total mass.
And this right here, this is the whole point. This is the magic of the mole. If a mole is just a number, how does it help us? Well, it's the bridge. It's the translator between the invisible world of counting individual atoms and the visible, practical world of weighing things in grams on a lab scale. It lets us count out a specific massive number of atoms just by using a scale. And that single idea, that connection, is what makes almost all of modern chemistry possible. It's the ultimate chemistry tool.